Good morning, everybody. This is the cycle of seminars from the Instituto de Astrofísica de Andalucía. And today we will have the talk by Dr. Yolanda Jimenez-Teja. And she will talk about unveiling the dynamical stage of massive clusters of galaxies, the intracluster light. So as a brief introduction of Dr. Jolie, she has her mathematical degree in University of Cadiz in 2003, then the Master of Geodesy, Geophysics, and Volcanology. Interesting. Also in University of Cadiz in 2006. Then the doctorship in physics and mathematics here at the IAA in 2011. And then she started a postdoc by the Junta de Andalucía from 2012 to 2013. Then she moved to Brazil as a postdoc, Jóvenes Talentos, in the program Ciencias Sin Frontera in Brazil at the Observatorio Nacional in Rio de Janeiro. And she was there from 2014 until 2016 as a postdoc. Then she moved to another postdoc as a postdoc, not at days, not at 10, excellent postdoc, under the Fundação de Amparo y Pesquisa do Rio de Janeiro, also in the Observatorio Nacional do Rio de Janeiro. And now she's here at the IAA under a postdoc individual fellowship, Marie Curie. She started here in 2020. Okay, last but not least, she received a prize. Sorry, I want to share my screen. It's a very important prize because she accepted the Lollipop Prize for her dedication to the seminar. So thank you very much, Jolie, for accepting this invitation and the motivation for doing that. And I think you can start your talk. Thank you.
Okay, let me share my screen because I'm now out, or at least I'm seeing your screen, not mine. Let me see. Okay, I'll open here again. Okay, can you see my screen?
Yes.
Okay. So yes, so I don't know if you can see my young face. So here it is a lollipop. I don't know if I really earned it or it's just a prize that René couldn't stop giving me because I'm pregnant. So I think that it's very difficult to say no to give a candy to a pregnant woman, but it's okay. And it's always a pleasure to give a talk here at home at the IAA. This time, I like to talk about my last work, my last accepted work that was entirely made with fundings by the European Commission within the frame of the Marie Curie program in the H2020 context. And it's about the relation between the dynamical stage of massive galaxy clusters and the intracluster light, joining our knowledge about that with the power of the RELICS data. So to start from the beginning, what is it, this intracluster light? So the intracluster light is a component of the galaxy clusters, also groups, that that is not very taken into account when we talk about these systems of galaxies. Traditionally, we always say that a cluster of galaxies is composed by the galaxies themselves, dark matter, and also hot gas. But there is a fourth component that is the intracluster light, which is this in this very beautiful picture of Virgo by Mijos. The intracluster light would be this faint, very low surface brightness light that is colored in an orangish tone, and which is like spread all over the cluster and is surrounding all the galaxies there in the cluster. It is defined formally as the luminous components made by these stars that are caught by the gravitational potential of the cluster, but these stars do not belong to any galaxy in the cluster. So these stars are like free; they don't have host galaxies to belong to, but they suffer the potential of the cluster. This ICL is very important. It's estimated that it can make up to 50% of the optical light of the total cluster, but it has remained almost unstudied for many years. But there was like a burst in the ICL, in the studies, like 15, 20 more years ago, more or less. So why is important the light from these free stars? First, because their mechanisms, its mechanisms of formation is intimately linked to the hierarchical process of operation of the cluster. So knowing the characteristics of the ICL can give us insights about the processes that govern the formation and evolution of the clusters. Also, to understand the metal enrichment of the intercluster gas, we do know that there is a lot of metals in the intercluster medium that cannot be explained a lot with the star formation rates in galaxies and the processes that move these metals to the intercluster medium. But if we take into account the ICL, is like the number much better. Also, the ICL is very important to constrain cosmological parameters, as for example, the omega matter. We do know that if we calculate the variance fraction or in clusters just using gas, although the gas represents the majority of the variance in the clusters, it's not enough to match or to be more consistent with the cosmological parameters calculated by other independent proofs. We also know that some supernovae have been found in the intracluster light, which can also help to the metal knowledge of the intercluster medium. And in general, the intercluster light is also important for people that is not interested in that are not interested in intercluster light. Like, for example, people that needs to know very precisely the photometry of the galaxies in a cluster or the morphology, etc. Where does this intercluster light that, in short, I'll sometimes call it ICL for short. So where does this ICL come from? So mainly there are four mechanisms that would be the violent relaxation after major mergers, especially with the VCG, although not only with the VCG. Also, the tidal stripping of luminous galaxies that are orbiting within the cluster. Also, the total disruption or shredding of dwarf galaxies. That is a mechanism that can produce a lot of ICL at high radius or high distances from the center of the cluster. Finally, in situ star formation, although this is not a very important mechanism, as it is supposed to contribute just with 1% of the formation of the ICL. Depending on the main mechanism of formation for the ICL, the resulting ICL or the stars that will compose this ICL will have very different properties, like different colors, gradients in colors, in metallicity, in age, or not. And those properties would be more or less similar to those of the stars in the galaxies of the cluster. Here, I'd like to show you a very nice simulation by Rudik, Mijos, and McBride, where we can see several of these mechanisms acting together. So I repeat the simulation. So as the galaxies interact then with each other, the two subclusters that we see in the simulation merge, we see how more and more stars are stripped out into the intracluster space, creating this cloud of gray areas that would be like the intracluster light, the stars in the intracluster light. So, okay, now we are convinced that the ICL is something like a sexy topic to study. We do know that it has been discovered, it was discovered by Zwicky in the 50s. So how or why the ICL has remained unstudied for at least 50, 60 years until the last 15, 20 years. So mainly for two reasons. First one, a technical problem. The ICL is very difficult to detect. It's very faint. It has a very low surface brightness. So we really need deep observations to really see the ICL, and moreover, to measure it with a certain guarantee that the errors are not ridiculous. Also, analytical problems, which would be mainly two. First one is, how can we disentangle the light of the stars that belong to the galaxies themselves from the light of the stars that belong to the ICL? So if we go back to this color image of Virgo, it's like one couldn't say easily where a galaxy, let's say, ends, more or less. Let's say this ends with quotation marks, where the ICL starts. Moreover, a second problem. Suppose that we have a good mechanism or a good algorithm to separate the light of the galaxies, of any galaxy in the image, from the ICL. It's the same for the VCG, for the brightest galaxy in the cluster? No, we do know that the ICL tends to concentrate, as it follows the potential of the gravitational potential of the cluster, it tends to concentrate around the center of the potential of the cluster, which usually coincides in a spatial projection with the VCG. So most cases we see that the surface in projection, the surface of the VCG matches somehow the surface of the ICL. And moreover, if the VCG has an extended envelope, it's not easy to determine the transition from this halo to the ICL, which usually occurs smoothly. So for all these reasons, it's very difficult, very, very complex to study the ICL, but we decided, oh, sorry, I think that I was about to forget. It's important to know that even this transition or this disentanglement is very difficult to be done. It exists. Many people believe that the ICL is just a continuation of the extended the galactic halo of the VCGs. And that's not true, as Longobardi proved in 2018. We can see here the velocity dispersion profile for M87, the VCG at the Virgo cluster. And here she gathered a lot of data from IFUs, from the kinematics of globular clusters, ultra-compact dwarfs, and planetary nebulae. Here we can see that the profile follows a decreasing trend. And if we consider all the tracers and all the data all together, the velocity dispersion starts to increase with a very, very strong inclination. However, if we separate the tracers between, if we split the tracers into those belonging to the ICL and those belonging to the galactic halo, we see that the galactic halo behaves as expected, and the excess in the velocity dispersion corresponds to the ICL. So indeed, there are different components, different kinematic components. It's very difficult to separate them using photometry alone. The ideal case would be using dynamics and dynamical data always, but of course it's something that we don't usually have at hand, so we need to do what we can with the data that we have, with the aim of developing an algorithm that was precise and free of assumptions about the ICL, as is typical surface brightness or morphology, etc. We developed in 2016 an algorithm that we call CYCLE. CYCLE stands for Chef's intracluster light estimator. In a nutshell, CYCLE separates the ICL from the galactic light using essentially two tools, which are the Chef's and tools from differential geometry, tools of curvature. So let's give a brief look into this. So here we have an example, the first example first cluster that we analyzed, that is the Pandora Cluster, Able 2744. And here you can see the original image as observed by the Frontier Fields program in the 814 filter. So first thing that we did was removing the light of all galaxies by modeling them and using these models to remove this contribution for the image. How did we model each galaxy on the image? Using a tool that we developed in 2012 that is called CHEFS. CHEFS is a mathematical orthonormal basis that is built using Chebyshev rational functions and Fourier series. There it comes name from Chebyshev and Fourier. We showed that joining these two analytical set of functions in a certain way, we could obtain a mathematical orthonormal basis that was very flexible, capable of modeling galaxies with any kind of morphology. And the only requirement is that the object to be modeled is smooth enough. For example, we cannot model saturated stars or objects that are cut in the borders of an image, or any kind of object that has a very sharp feature. So here to show an example of the power of the CHEFs, here we can see a very detailed galaxy and Spitzer image with a lot of detail of a spiral galaxy. And here you can see the original image, and this is the CHEF model. The points that are missing there are point-like sources, so maybe stars that CHEFs, as I said, are unable to fit. And here you can see that the model is very, very precise. Maybe we can see some differences here in these outer areas here, but in general, they perform very, very well. So using CHEFs, we model and remove all the galaxies in an image. But again, for the VCG, we need to find this transition from the halo to the ICL in a different way, because CHEFs alone are not, would model everything together without knowing where to stop the model, let's say. So for the particular case of the VCG or the VCGs, as seen in the Pandora Cluster, we re-added the models of the VCG, the CHEF models, to leave that part, that region of the image completely untouched. And we did a more thorough analysis of this region. What we did was analyzing the curvature of the composite surface made by the VCG and the ICL. Which is the curvature? The curvature is a characteristic of each point in a surface. And it measures like the change in the slope that the surface suffers in that exact point. Here we can see a toy model of a surface that has like a bump that is coming toward us. And here we can see four different types of curvatures that are very traditional, very well known in differential geometry. We can see that the minimum principal curvature is able to catch the shape of the bump that is coming toward us in a very reasonable way. So we thought that maybe using this curvature parameter could help us to know where the limits of the VCG dominated area are. And indeed, we did the exercise with the Pandora Cluster. Here you could see the curvature map, the principal minimum curvature map, and the points here in the curves of blue points here would be the points where the curvature changed most. Well, that would be the points where this transition occurs. And finally, we removed the contribution of the VCG, but constrained to the limits of these blue lines. We used simulations to see if this purely geometrical approach was reasonable, and we created models and simulations of clusters with different configurations for the VCG and the ICL. Here you can see 3 examples where the VCG is plotted in red and the ICL in blue. So we started from what is obtained as the average cluster in the redshift range from 0.2 to 0.3 as found by Zivetti and collaborators. And for this average cluster in this interval of redshift, the error committed by cycle is very, very close to 0, a very, very low error. As we increase the complexity to find this transition from the VCG to the ICL dominated areas, like making the ICL and the VCG more and more similar and with more similar slopes, the error increase, the error in the determination of this transition is higher, of course. And when the VCG and the ICL are very, very close, are very similar, we found a total error of 10%. From that point, the error strongly raises. And for example, for these configurations, it would be completely impossible for cycle to find the transition, not only for cycle, for any algorithm, because here we can see that the ICL is completely embedded inside the VCG. So it would be like a very, very theoretical and impossible case to analyze. Here I'd like to show you another exercise that we did with a BGG, that would be the brightest galaxy in a subgroup in the Virgo cluster, that is M49. We knew that the transition from the VCG to the ICL was determined using tracers kinematically, specifically using planetary nebulae. So we applied cycle to this galaxy in Virgo, and we found first that the ICL, let's say underlining this VCG, was not homogeneous, but it had like 2 brighter regions on the north and more or less on the south. And we found that the average radius of the VCG dominated region would be around 41 kiloparsecs. Comparing that with the work of Hart and collaborators, we saw that they also identified 2 regions or 2 quadrants with brighter planetary nebulae, exactly matching with the brighter areas of the ICL that cycle had found, what made us very, very happy and very, very shocked when we saw that. Also, they determined probabilistically the transition from the VCG to the ICL as something in between, more or less. It would be like the crossing of the points with this horizontal line, and that would be around, I don't know, 55, 53 kiloparsecs, which is pretty consistent with our measurements considering the error bars. So it seems that cycle works when compared to kinematical analysis. It seems that that is also consistent. So we decided to apply cycle to a higher sample of 11 clusters, all of them observed by the HST, mainly from CLASH and the Frontier Field programs. They had in common that they were all massive, spanning the redshift interval between more or less 0.2 to 0.55. And they all have had their dynamical stages very well defined by different proofs, like, for example, the X-ray distribution and morphology, the presence or not of a cool core, the distribution of velocities of the galaxies, the presence or not of radio halos and radio helix, and presence of substructure, for example. And in this work that we did in 2018, we did 4 things that were completely different from what was usually done previously up to that date. First, we use cycled instead of any other technique to separate the ICL. Also, we split the sample into relaxed or passive and merging clusters, which is something that it wasn't very taken into account when in the previous studies of the ICL. We also decided to measure the ICL fraction. The ICL fraction is the ratio between the flux in the ICL and the total flux of the cluster. So we decided to measure the ICL fraction in different wavelengths. Previous works in the literature were usually limited to 1 or 2 filters, that's all. But we decided to use more filters. And another difference is that we measure the total ICL fraction. We were not restricted to a fixed radio, like, for example, a certain fraction of the video and radios or something similar to that. But we measure the ICL up to the limit where we can detect it safely. It's like comparing in a galaxy in a aperture magnitude versus a total magnitude. So this is exactly the same, but with the ICL. And doing this work, we saw that here we put all the ICL fractions that we measure for these 11 clusters. We measure the ICL fraction in 3 different optical filters of the HST. We put all the results in the rest frame. We saw that for the subsample of relaxed clusters, that is the subsample with markers colored in blue, the ICL fractions that we found were lower, and they were nearly constant within the error bars. However, for the subsample of merging clusters, which are the symbols in red, we found that the ICL fractions were significantly higher, a factor of 2.3 on average higher than those of the relaxed clusters. And also, they weren't constant. They showed this peak that it was like from 3,500 angstroms to more or less 4,800 angstroms. The explanation that we found in this work of 2018 for this was that for the subsample of relaxed clusters, the main mechanisms of ICL was the tidal stripping of the galaxies that were passively evolving within the cluster, orbiting towards the center of rotation of the cluster. So at the end, the populations of the ICL and the galaxies, the member galaxies, somehow matches the ICL fraction, which is like this relation between the stars in the ICL and the stars in the total cluster, somehow were constant along different wavelengths. However, for the subsample of merging clusters, there is like an enhancement in the ICL fraction that is provoked by the merger itself. So there is this additional contribution of stars that are liberated into the ICL, originated by the merger itself. Especially it is seen that younger or lower metallicity stars contribute to the ICL to form this peak at these wavelengths. We later confirmed with a work by Morishita and collaborators in 2017 that for the frontier fields clusters, which are all mergers, there was an excess of A and A type stars in the ICL, which and we here plot the wavelength intervals where the emission peaks of these stars are more or less located. And we saw that more or less this was consistent with the peak that we saw analyzing the ICL fraction alone. So we were very happy with these results, and we decided to do a larger study. This work was fully funded by the European Commission, as I said, and the main idea was joining the power of cycle with the power of RELICS. RELICS is Hubble multi-treasure program, multi-orbit program, sorry, that has observed 41 galaxy clusters with HST and high quality data. So all of them are massive. So it's the same that we had for our previous sample of 11 clusters, and they span the redshift interval between 0.2 to almost 1. So the idea is studying the evolution of the ICL with redshift. We have started with the cluster WHL 0137, which is a redshift 0.56, so which is at the high end of our redshift interval that we studied before. These RELICS data were the first ones for this cluster with HST. This cluster is very, very, very interesting because it has a length arc of about 15 arc-second long, which makes it the longest arc at redshift higher than 6. And it is also interesting for many other things that will be published soon in a paper by Brian Welch and collaborators. Stay tuned. As this cluster was so interesting, we had many filters to work with enough depth to see the ICL. So we had 9 bands in total, 4 in the optical and 5 in the infrared. And here you can see the original, a color composite image of the cluster and a color composite image of the ICL after this cluster was cycled or was processed by cycle. Here you can see how the ICL nicely extends around the main core of the cluster, and its smoothness and its colors. And also we measure the ICL fraction at these different wavelengths. Here you can see the same plot as before, but here we have added the new black points, which corresponds to the cluster WHL 0137. First, we saw that going to the optical, the points nicely follows the peak as the previous merging cluster. So we determined that this should be a merging cluster also. Later, we saw that that was consistent with the X-ray distribution of the cluster, which also showed that this is a merging cluster. Another new thing that we did was going to the infrared. That is something that we hadn't done before, so we didn't have results in the infrared to anchor our new results about this cluster. So first thing that we noticed is that the ICL fractions in the infrared were significantly higher than those in the optical. At first, we were puzzled, and we thought that that could be the result of any kind of systematic that was affecting our measurement. So we ruled out a bunch of possible systematics, like, for example, the contribution of the contamination by the zodiacal light and the Earth shine. We checked that the observational strategy followed with this cluster was good enough to minimize the possible effect of this contamination. Also, even though the observational strategy was very good, we compare our measured backgrounds for this image with models of the zodiacal light, and we saw that there was no trend between the two measurements. So that meant that the images were indeed free of this possible contamination. We also checked if the images could be suffering from some persistence. So Borlaug and collaborators showed that for the wide field camera 3, the infrared camera in the HST, the persistence is an effect that can highly affect the studies of low surface brightness sources. Persistence is when some light from previous observations remain in the detector, so they appear somehow in observations afterwards. However, we calculate models with a loopback time of 96 hours to see if this could be affecting our observations, and the answer was no, and the possible effect was completely negligible, of 0.002% for the worst filter. And also, following Borlaug and collaborators, we calculated new flats for our images. We calculated sky flats and compared them with the official mast flats. We indeed saw that our newly reduced images were flatter than those provided by the official mast pipeline. These are for comparisons between the official reduction and the new reduction. The differences are not very significant for the infrared. They are for the optical. We can see how the new reduced data is flatter, and in fact it preserves more. The ICL is not so aggressive. It doesn't misidentify the background with the sky with the ICL as much as the official mast pipeline does. But considering that we are measuring the ICL fraction in its whole extension and not limited like by a small radius, and that also that we are using the ICL fraction, which somehow dilutes the effect of this flat. The maximum difference of the maximum error that we found in the ICL fractions, considering the new flats, was as high as 1.26% for the worst filter. So again, this wasn't an issue to explain our higher infrared ICL fractions. So we tried to see if maybe dust reddening could be playing a role there in these enhanced redder ICL fractions. We first checked that galactic and intergalactic dust contribution was very low because the WHL 0137 is far from the galactic plane. And also, even if this contribution were significant, that would enter as a multiplicative term into the ICL fraction, because it equally affects to the ICL and the other galaxies and the member galaxies of the cluster. So it would be canceled out. Also, we thought that maybe intracluster dust was reddening the intercluster stars. But this dust is not expected to survive in the ICL much more than a few thousand years. And its contribution would be negligible, especially at the very near infrared. So it's ruled out also. We also checked if cold gas filaments originated from warm galactic outflows could be contributing with some dust, because we know that this dust can weather the sputtering depending on the size of the grain. But even if this effect was present, it would be confined to a scale of tens of kiloparsecs. That for a cluster that is a redshift 0.5 is again negligible. We couldn't see that. So it seems that these ICL fractions, these very high ICL fractions, are for real. What we are seeing here is a mix of stellar components in the ICL. We can see a bluer component that is intimately linked to the emerging dynamical stage of the cluster. So these are stars that are fueled into the ICL due to the tidal stripping of infalling galaxies, high speed encounters due to the merger, and the total disruption of dwarf galaxies. While there is a redder, no redder population, but there are redder stars that maybe were put there at higher redshifts during the process of formation of the cluster itself, or maybe these are just ICL stars, all past ICL stars that are aging, or maybe these are stars that are stripped from the extant passive galaxies that belong to the cluster as they evolve towards the center of potential. Or it can be even ICL that is preprocessed in groups, infalling groups that are merging with the cluster itself. We know that this ICL preprocessed in groups it should be redder, and in fact we do know that as the interactions within the group strip out stars, and the group falls into the cluster potential, the RAM pressure stripping is increased, and somehow it appears some regions with some H2 regions, and this appeared in the reddest parts of our wavelength interval. Also, it could be the presence of emission line nebulae. Also, this again would be a very minor effect confined to a few kiloparsecs in the center of the cluster, but it's a possibility. And well, to sum up, we in past works showed that the ICL fraction can be used as an independent indicator of the dynamical state of the clusters. We know that passive clusters or relaxed clusters have ICL fractions that are radically different from those in emerging clusters. We going to our last work on WHL0137, we know that it can be classified as a merging cluster, which is consistent with the X-rays. Going to or exploring the infrared, we saw that the ICL must be a mixing of different type of stars and different mechanisms that are feeding the ICL simultaneously. Well, I didn't talk about this, but we also discovered that WHL0137 has the potential of becoming a fossil group, so it would be considered a fossil group progenitor. And finally, I think that this work is very important because it's the first step to show that the RELICS data is very valuable for ICL studies and low brightness surface purposes. Well, we continue with our work in this way. And thank you for your attention. I'm open to questions.
Thank you very much, Jolie, for this nice talk. And now the talk is open for questions. Please, all the people, raise your hand. For doing that, go to the reaction button at the bottom of the screen and then press there the raising hand icon. Okay, who will be the first? I give a lollipop for the first question. Oh, Florence. Okay, go on.
Hello, thank you for this lovely talk. I don't really need a lollipop, but you can give it to Yoli for me.
Perfect, I will do it.
I was interested by the fact that you find a higher fraction of intracluster light in the infrared. We also found the same in one of the clusters that you mentioned here, which is MAX 0717. And there was an analysis that was done by my former PhD student, Amael Elien, and he developed a code to extract the ICL based on wavelengths. And he applied it as a first try to MAX 0717 in 4 HST bands. And so he didn't detect any ICL in the blue. And then in I think it was the 606, 814, and then one of the infrared filters. And as you go redder, the intracluster light fraction increased. So are you going to do this for other clusters as well in the infrared?
Yes, for sure. We do have the infrared filters for clash data. It's something that we just didn't do. I don't know. I don't have an answer for.
No, I'm just asking if you are going to do, if you plan to do it, because it would be nice to have the same result for a sample of clusters rather than just 2.
Yes, for sure. We are considering all the RELICS data, the RELICS sample, and also the clash sample, because they all have all these panchromatic data of the clusters. To give a flavor of our current work, now I'm studying especially in the infrared, of course, the ICL fraction in the two highest redshift clusters in the redshift in the RELICS sample, which are more or less at 0.9.
Ooh.
So my intention is double, is to see is this enhance of higher infrared is ICL fractions in the infrared still appear there, and also to see if these behave, or this difference between merging and relaxed clusters is ubiquitous, or it only appears at redshift intermediate to lower redshifts. So that's our current work, which is in process.
Okay. Very nice. So we will be waiting for your results.
Thank you.
If may I ask another question?
Sure, go on.
Okay, then you said just at the end in the conclusions that WHL01 something is maybe the progenitor of a fossil group. And could you say why?
Yes, the point was that as we calculate ICL fractions, we need to perform some cluster membership. For the RELICS clusters, we don't have generally spectra to calculate this cluster membership. So we had the help of a collaborator who has a machine learning algorithm for classifying the galaxies in between cluster and between members and non-members in a cluster. And when we were having a look at the color magnitude diagram, we noticed that the magnitude of the VCG was rather far from those of the other cluster members. So first we checked if it followed the criteria to be a fossil group, the two magnitude difference in brightness with the second ranked galaxy, between the VCG and the second ranked galaxy. It didn't, but we followed previous works that made a huge assumption, which is that the system is going to remain isolated up to date, and that all the galaxies that has the potential to merge with the VCG in this look back time are going to join their stars to the VCG, and only the VCG, that no fraction of these stars are going to the ICL, which we know that is a very huge assumption.
Yeah, that's not true.
Yes, exactly. But if we do the numbers and calculate with dynamics, how many of these galaxies have the potential to merge with the VCG, and assuming that they will incorporate all their stars to the VCG after this look back time, this system would become a fossil group. So it has the potential of being a fossil group progenitor, which makes it even more interesting.
Thank you very much.
Thank you to you.
Okay, there is a question in the chat made by Wei Wang. If the high ICL fraction in the unrelaxed clusters than the relaxed clusters related to how the ICI is measured?
Not really, in the sense that the algorithm is the same, and also the radius used to measure the ICL fractions is essentially the limits that the own data impose. So it's not like as relaxed clusters have some kind of symmetry or are more concentrated in general. We are measuring ICL fractions in smaller radii or in a different way. It shouldn't be a difference as we are using total magnitudes. It shouldn't be a difference because we are using ICL fractions, which makes lives easier because we are free of a lot of systematics that can affect another ICL measurements, as for example the effect of the PSF or color gradients, etc. So in principle, there is no difference. In fact, when analyzing a merging cluster that is a higher redshift, how they look in the bluer bands, as Florence pointed, is very difficult. There is very few ICL there, so it's kind of similar to what we see in a relaxed cluster, and still the measurements, the resulting measurements are radically different. So the answer should be no.
Okay, thank you. I think the answer is way one. Is if you want to add something, you can do it in the chat.
Yeah, may I directly speak? Sorry. Okay, so what I mean, the measurement for the ICL is different. It's not talking about your method. It's talking about the intrinsic difference between those merging clusters and the relaxed clusters. And you have said that those stars from merging clusters can be younger, the ICL stars, than those in relaxed clusters. And the other thing that comes to my mind is that if you think about the merging system, and you may select those tails when these galaxy merge together, and you will see a tail of those stars during this merger event. And is this included in, I think, included in your ICL fraction? Is that right? And in theory, we're talking about theory that maybe those stars is still physically bonding to the merging galaxy. And that is what I'm talking about, the intrinsic difference between those different dynamical clusters, and may have some effect on this measurement.
Okay, I see. Now I understand your question. So the point here is that somehow it's tricky to interpret the ICL fractions. The fact that we see a peak for the merging clusters doesn't imply that we have younger or lower metallicity stars in the ICL for merging clusters, and these stars are not present in the relaxed clusters. Mm-hmm. It means that the fraction or the amount of these stars in the ICL compared to the amount of these stars in the galaxies is higher for merging clusters, but they exist in the two situations. So, for example, as the galaxies passively evolve towards the center of potential of the potential of the cluster, they will lose the stars in the outer regions. Mm-hmm. These stars are mainly bluer at this redshift range, and as they evolve towards the VCG, the stars that they are losing are redder and redder. But somehow it's like the the amount of these stars in the ICL, these bluer stars in the ICL, and the amount of these stars in the galaxies balanced for passive clusters. But when you have a merger, there is an additional mechanism that mainly increase the fraction of bluer stars. So obviously the environment is provoking that the final ICL should be bluer in the case of the merging clusters, or the gradient in color or age or metallicity should be steeper for merging clusters than for relaxed clusters, although this is an analysis that I haven't done, but it should be interesting to do. But what I want to say is that it's not that these passive clusters don't have bluer stars in the ICL, but the amount is more comparable to the amount of these stars in the galaxies of the cluster.
I see your point. It's maybe more clear that if you show the profile of those ICL, and then we can see directly that how this stripping effect is actually showing up in this ICL fraction. Thank you. Very interesting.
Thank you. Thank you to you.
Thank you. There is another question. Rosa, please go on.
Hello, Jolie.
Hello.
Congratulations. Very nice talk. Well, I have a question related with the assumption that probably you can explain the intracluster fraction in the infrared by the presence of emission line. So you are talking about the emission line by massive star or by planetary nebula, or what? Or what kind of the contributor or tracer are you talking about?
Yes, the main mechanism that I consider to try to explain these higher ICL fractions was based on planetary nebulae. Basically, because for galaxies in low redshift clusters, we can see these planetary nebulae. Of course, for such a high or intermediate redshift cluster, we wouldn't see this contribution, but still their effect should be noticed somehow in these higher ICL fractions. Also, the ICL that is preprocessed in groups and is incorporated into the ICL as the group merge with the cluster present emission H2 regions of H2 emissions, and even it has been seen H1 emission. All of that would be appearing in the infrared. Of course, I cannot quantify if this effect is the contribution or the proportion that this effect could have compared with the others, because I really think that the main mechanism of formation for these redder stars it occurs at very much higher redshifts during the process of assembling of the VCG and the cluster itself at redshift 1 or even higher than 1, because the few works that we have in the literature showing the ICL with very, very high redshift clusters, 1.2, 1.5, show a very considerable amount of ICL. We can see a lot of ICL at high redshift, and this is mainly red, very red. So I think that this is the main mechanism, but still the other mechanisms should be additioning something.
Okay, thank you.
Thank you. To you.
Thank you, Rosa. Thank you, Jolly, for the answer. No more questions. I think it's enough, and we can close the talk here. Thank you very much.
Thank you.
Jolly, for this wonderful talk. And to everybody, see you next talk next week. Thank you very much.
Thank you to you all
Thank you.
for your attention, and to Rene for the lollipop.
I stopped recording now, so now it's off the record.
Okay. Okay. Thank you.
Muy bien, excelente.